We are now discussing process capability analysis, the different aspects of process capability analysis. In this presentation, I will be focusing on the process capability analysis procedures and what are the approaches we need to adopt for carrying out a process capability study. And obviously there could be different approaches, and these the particular approach we select based on in which form we are able to collect data. Now here, when we talk about approaches for determining process capability related to a particular process, either you are allowed to use the individual observations, so that is the first case, or in many a time the control chart information is also made available, so you can also use control chart information. Okay, so I am going to elaborate the approaches you adopt or you use for carrying out process capability analysis. Now certain important points you should keep in mind. We have identified a process for which process capability analysis is to be carried out, and obviously we are running the process, and while you run the process, in order to produce something, say parts or the components or the product itself, and what you need to know, that is, what are the process parameters. So identification of the process parameters is a must, and then how do you relate this the process parameters with the kinds of operations you carry out on a particular process. So this knowledge is a must. Now assuming that you have this knowledge for a particular process, now three kinds of analysis we need to carry out. First one is estimation of the process parameters, and as I have already mentioned that there are two important process parameters in this context. One is the process mean, that you must know, and the second one is the process standard deviation. There could be other process parameters also, but in majority of the cases we focus on two important process parameters, and we must get an estimate for them. Is it okay? That is the first step in process capability analysis. So these two process parameters are process mean and the process standard deviation or the process variance. At the second step, what we try to do, we identify the form of the distribution of the quality characteristics under consideration. We are already aware of that the quality characteristics or the types of the random variable you come across. Now there must be some distributional assumption for a particular random variable, and the quality characteristic, the values which you get, they are all random variables. So the next important the aspect we look into, that is to identify the form of the distribution. And looking at the form of the distribution, now you may hypothesize that what could be the type of distribution for the given quality characteristics, like whether it may be in the standard form, like normal, like exponential, like Poisson, etc., or it could be in the empirical form also. Is it okay? And the next step which we carry out, we are concerned with, that is estimating the proportion of the non-conforming output or the product. Means ultimately this proportion of non-conforming output actually indicates the process performance. That's we have already pointed out. Okay. Now while you estimate the process parameters, now let us focus on estimation of the process parameter, like the process mean and process standard deviation. There are few observations, there are few conclusions we may make. Like in majority of the cases, we need to estimate process mean and the process standard deviation. This point we have already mentioned. And then once this is known, that means the estimate of the process mean or estimate of the process standard deviation, then distribution of the quality characteristic is to be known after constructing the frequency distribution. That means the first exercise you should carry out when you start collecting data. Suppose 100 such the data points you have collected from a running process related to a particular quality characteristics, okay, then of the component, and then what you try to do, that means first you construct the frequency distribution, and looking at the form of the frequency distributions, you may conclude at the initial stage subjectively that what could be the possible distribution of the quality characteristics. We may go for hypothesis testing to conclude a possible distribution in standard form under a given level of significance. Like we might say that my level of significance is say 0.01 or 0.05. So the distribution is assumed to be normal distribution. Is it okay? So for that the standard procedure is hypothesis testing. Okay. So already we have mentioned that in statistics there are two kinds of statistics we have. One is descriptive statistics, and the second one is the inferential statistics. So here in this case we will go for hypothesis testing, that is a part of inferential statistics. Okay. Now the first thing you must ensure before you carry out a process capability study for a process that sufficient data are made available and you are allowed to collect these data. So while collecting data for estimating the process parameters, we may find two situations. Okay. So what are these two situations? The first one is you just go to the process, you consult with the concerned person and you ask him or her what kind of data related to a particular quality characteristics you are collecting. Okay. As the production process is on. So the individual observation, say quality characteristic is a random variable x, and you might say that okay, last 1 week's data or last 1 fortnight's data are made available. So these are the individual observations. Okay. And how to use these individual observations for process capability analysis. Okay. So this could be one case. The second case is that is the control chart information is available. As you may be knowing, and we have always emphasized this aspect, that whenever you conclude that the process is in statistical control, okay, and then you are supposed to measure the performance of the process. So the process capability is indicative of the process performance. This point already have mentioned, but make sure that the process is in statistical control. Is right? Now, how to make the process or how to achieve this condition or the state of statistical control? Obviously, you need to use certain tools, and these tools which you must be used for online real-time control of the process. Okay, so the control chart is one such tool. So prior to estimating the process parameter values, is it okay, in a control condition, so it is assumed that you have been using the control chart for substantial period of time, and you have achieved this condition, that is the state of statistical control, right. So, obviously, in a majority of the cases, in almost all cases, you will find that the control chart information is already made available. And if you refer to this control chart, the information or the data, obviously you will be in a position to carry out the process capability analysis. Okay. So, the second situation is very, very common whenever you carry out process capability analysis. One main condition you need to keep in mind. So, this is to be kept in mind, this important the condition that the process capability analysis is meaningful only when the process is in statistical control. Is it okay? This point we have been emphasizing all the time. So, control charts is used to achieve this state or this condition, and hence in majority of the cases control chart information is made available. So, this point already I have elaborated. Now, let us talk about estimation of the process mean. Okay. So, process mean, the notation is mu, and as you may be knowing that we always say that the process mean, okay, remains unknown. That means it is never known. What you can estimate, that is a good estimate for the process mean. Now, how do you get a good estimate? Obviously, from the population or from the process, you have to draw a sample. Okay. And how to draw the sample? There are many procedures. Okay. It could be a probability sampling procedures, or it could be a non-probability sampling procedures. But what we say that make sure, whatever may be the procedure, make sure that the sample or the subgroup is representative of the population. That means the kinds of characteristics you have to identify the characteristics of the population, and you must have the same sort of characteristics in the sample. Is it okay? So, that is to be ensured. And another condition you must ensure in many cases, that is the condition of randomness. Is it okay? So, there are different procedures. So, in course of time we will be telling you, particularly when we will be discussing acceptance sampling. Is it okay? So, that is another important topic in quality design and control. We will be elaborating on this concept, that how to draw the sample, what sort of procedures you have, so that the sample becomes a representative of the population or the process. So, obviously, here from the population or from the process, that means what is the population? That means suppose the total the number of produced units in a shift, say 8-hour duration, is said 2000 units. Is it okay? 2000 units of a component of a part. So, that is basically the population size. Obviously, it may not be necessary or it may not be practical to get 2000 say the data points. So, what you try to do? You try to get a sample representative of the population, and now you consider the data points in the sample. So, here what you try to do, that means the process mean mu is estimated as sample mean, and the notation is x bar. You just always we have these notations. You refer to x bar control chart. Okay, you will find that these notation you use. So, sample size n is restricted to 50. Okay, though sometimes we say that n is greater than equals to 30 may be considered to a large sample. So, the sample size should be as large as possible, and in a running production system, in a running process, okay, getting a sample size of 100 may not be a problem. Is it okay? So, this we have observed, like the practitioners, they will say, okay sir, give us just the 2 days time. Okay, so, I will have a sample of 100 units or even 200 units. Is it okay? So, in a running production system, a repetitive manufacturing, this it will not pose any problem. Okay, so the sufficient number of data points you will have in the sample. Next, what you do? You just calculate the sample mean. Is it okay? The sample mean, that is sigma I equals to 1 to n xi divided by n. Is it okay? So it's an arithmetic mean you calculate. Next, what you do? That means a frequency or related frequency histogram is constructed for the quality characteristic. Is it okay? So this is so the next exercise you carry out. Now, before a distributional assumption is validated through hypothesis testing. So you go for the goodness of fit test. It's okay. Now we say that the random variable may be assumed to be a normal random variable. So how do you conclude this? Obviously, go for hypothesis testing. Is it okay? And like say there are many kinds of the tests you have, like say the chi-square tests you have. So later on we will be referring to that. And but prior to the carrying out this goodness of fit test, okay, a visual check can be made through histogram plotting. That means first you look at the histogram, okay, and then you conclude that what could be the possible the distribution. This is subjective, but the subjective assessment is a must before you go for objective analysis. Is it okay? So in this case, if you plot the histogram, so you will have some informations like by looking at the shape, you may conclude whether the whether the distribution is unimodal or multimodal, whether the distribution is symmetric or not. Is it okay? What is the pickedness of the distributions? Is it okay? And similarly, the skewness, whether it is skewed to the right or the skewed to the left. So these sort of observations, okay, or say subjective judgment you may make regarding the distributions, regarding the random variable under consideration. So this is a must. So characteristics of a distribution such as skewness, is it okay, and kurtosis coefficients can also be calculated. Is it okay? Like say in terms of the moments of the distributions. That means as the first moment, second moment, third moment, fourth moment. As you collect more sort of information, you may be in a position to compute the third moment of the distribution as well as the fourth moment of the distributions. Okay. So when you calculate, you have the data with which you can calculate the third moment. Obviously, the skewness coefficient you can calculate, and similarly, if you have sufficient information so that you can have the fourth moment, then obviously the kurtosis coefficient also you can calculate, so that you may have a fairly good idea about the variability, about the characteristics of the distribution. Is it okay? So this exercise we do routinely. Next, what you try to do, that means we calculate along with the mean, we also calculate the standard deviation. Is it okay? So the standard deviation part, as you know, that the sample standard deviation, that is you have n number of data points, and make sure that that is an unbiased estimate of the standard distribution you must have. Okay. So I have mentioned about the mean, but subsequently with the same set of data in the sample, you calculate the sample standard deviation. Is it okay? So what you try to do, that means individual values, you must subtract from the individual values the mean value, that means x bar, and the square of this deviation, and you add them for all the individual values, and then you divide it by n minus 1. Is it okay? And that is essentially the variance, and then for the given sample of size n, so you calculate this positive square root of the variance, and that is the standard deviation. Is it okay? So so you can get that formulation. There will be absolutely no problem. Is it okay? So with respect to the x bar, you calculate the the standard deviation, and first you calculate the variance and then you calculate the standard deviation. In many cases, central limit theorem is valid and hence normality assumption holds, particularly for running production systems, and the system is such that when you get the value of x is basically this value, or say the notation could be y, that is say the output, say the quality characteristic. Now in many cases you will find in the repetitive manufacturing, or for that matter any kinds of manufacturing systems, when this value you get in the the downstream stage. Is it okay? Now obviously there are many factors affecting the value of y, okay, factors in the upstream process. There are many factors affecting. If this is the this is the situations, that means you may always assume that the y or the output quality characteristics may be normal. Is it okay? So this is the physical basis you must be aware of before you go for normality assumption. And the second one is the central limit theorem you should be aware of. Is it okay? Because many sorts of tools and techniques, the expressions you come across in quality control and in quality control exercises, and the basic assumption is the normality assumptions. Okay, there are cases where you may have non-normality assumptions, but in majority of the cases you assume normality. Central limit theorem states that whatever may be the distribution of x is a random variable. The distributions of any the statistic of x, whether it is a mean or whether it is a standard deviation, may be assumed to be normal when the sample size is very large. So we are dealing with a large sample size running production systems. Okay, so how do you define the process spread? I have mentioned the process spread when you assume that upper natural tolerance limit lies say at say 3 sigma away from the mean with this assumption, and similarly the lower natural tolerance limit related to a particular process lies at say minus 3 sigma away from the mean, that means on the other side of the mean. So if this assumption is valid, then the process spread is obviously 3 sigma plus 3 sigma, that is 6 into sigma. Is it okay? So this is just one case. Otherwise it is essentially 2k sigma. 2k sigma. Now the k could be in this case we have assumed the value of k is 3, but it may be in a special case you may assume it to be say 2.5 or say 2 or even 3.09 and many. So depending on suppose you will face a critical situations, or say suppose the specific situations. So the value of k could be 2.5 or choice is yours, but otherwise unless otherwise specified you assume it to be 3. So that's why it is 6 into s. So what is s? S is the sample standard deviation. Why not sigma? Because sigma value, the actual value of sigma is never known. Okay, what is known is actually the sample standard deviation, and the sample is assumed to be a representative one. So obviously the natural tolerance limit will be x bar plus minus 3 into s. That means here the mu is replaced with x bar, that is the sample mean, and sigma is replaced with the sample standard deviation. So if the process is centered, we have already defined what is the centering of the process. The process capability Cp or process capability ratio, it is also known as PCR. Cp is given by USL minus LSL. That means this is a two-sided specification limit, double specification limit, for which the upper specification limit and the lower specification limit, these two values are known, divided by 6 into s. So the probability plotting method can also be used for knowing the distribution of the quality characteristics. So this is another method. That means like say many a time if you want to the test for normality. So why don't we use normal probability plot? So the probability plotting method is also widely used, is right. It's like, so there's few simple steps I will explain. That means suppose you deal with n number of observations, okay, x I varies from 1 to n, that is the situation. What actually you have to do, that means you have to rank them. That means from say the highest to the lowest one, you have to rank them, and then the ranked observations, that is ith observations is the ranked observations, okay, and then against a ranked observation you calculate fi, is it okay, that is I minus 0.5 divided by n, okay. Why it is 0.5? There is a rationale behind it. So as a student, as a learner, okay, you must know how did you get this 0.5, is it okay. So please find out the reasons of that why we subtract 0.5 from I, why not 5, why not 50 and all those, how do you get these values 0.5. So there is reason behind it. So I expect that the student will be knowing the exact reasons, okay. Divided by n, that means n is the total number of observations, So 100 fi value is plotted against each I, and if the points plotted are on a straight line, the distributional assumptions may be valid, is it okay. If the normality assumption is valid, by using a normal probability plot, is it okay, we may, that means you have to use the log scale basically, we may estimate the mean and the standard deviation. So what is that estimate? 50th percentile point is the mean, and 84th percentile point is 1 sigma away from 50th percentile point. This is 1 sigma, okay. When these estimates are known, we calculate CP, CPK and CPM. Now this is one aspect, that means you are dealing with individual observations. When you use the control chart information, is it okay? Already you have been using a control chart, and by using the control chart you conclude at this point in time when the process capability analysis has started, you assume that the process is in statistical control. That means the process behavior is not being influenced by the assignable causes or the external factors, or the assignable causes. When control chart information is made available, in many cases we do, that means the first exercise we carry out, are you in a position to apply the control chart? If you are successful in using or in developing as well as using control chart for your process, then the next question comes, okay, you have been using the control chart, very nice, but are you in a position to measure the performance of the process? Is the performance of the process improving? So obviously you have to carry out the process capability analysis. So this is the context. So in almost 100% of the cases, what we have found, that the control chart information is available. We can estimate the process mean and the process standard deviation by referring to information obtained in a particular control chart in use. So it's very simple. When variable control charts are used, as you know, there are two kinds of control charts we have been using, like say variables control charts. So the variables control charts, using the variables data which are measurable, for which gauges are used or the measuring instruments are used. So you estimate mu and sigma of the processes as, if you use R and X bar control chart, as I have already pointed out, that these two control charts must be used simultaneously. Okay, if someone say uses only R chart or only X bar control chart, okay, so absolutely the purpose is not served, is it okay? So the first you use the R chart, and then with the same set of data, okay, you use for constructing the X bar chart, and you start using X bar chart. So if you've been using it, obviously what is the estimate of mu, process mean, that is X double bar, that means the mean of the means. Is it okay? So this already you have already computed. Similarly, what is the sigma, estimate of sigma, that is an estimate of the process standard deviation, that is R bar, already you have computed while you refer to say R control chart, divided by D2, and D2 is basically a control chart factor control chart related factor D2, and it's a function of n, and you can read this value from the control chart factor table. Is it okay? Similarly, instead of using R control chart, suppose you use S control chart. So what is the estimate of process mean is X double bar, and estimate of the process standard deviation is S bar by C4. Again, C4 becomes a function of n. If you use when you deal with so the individual observations or the individual units, that means sample size is 1. Obviously, MR, that means moving range control chart, and X control chart you will be using. So what will be the estimate of mu, that is X bar. Is it okay? The individual observation, sample size is 1 for each sample, and the estimate of sigma is MR bar by D2. Is it okay? So when you use attributes control charts, suppose you are using P control chart, so the process capability is P bar. If you use C control chart, process capability is C bar. Okay. If you use NP control chart, that means the sample size is constant, the process capability is n into P bar. You refer to all these control charts, and U control chart is U bar. That means these are basically the center line. And if you use capital U control chart, demerits per unit, okay, control chart for controlling. So this is capital U bar. Upper control limit of any control chart is the estimate of the worst quality expected from the process. It's clear. So here directly the measurements are missing. Is it okay? So you are dealing with the attributes data. So what you say, that here is an attributes control chart. I know that what is the center line. So the center line is indicative of the process performance. Is it okay? And similarly, you have the upper control limit. So upper control limit is basically indicating the worst possible quality level. Is it okay? So so these are the ways you can estimate the process capability under various situations. Okay. So we'll deal with the other aspects of the process capability in the subsequent lectures.